Dr. Acton as he shares his insights and experiences concerning this amazing piece of technology.
Everybody hear me okay? Seems up here it's got quite an echo, but someone will worry about the sound, I guess, if it's not working out for. All right, great. It is fantastic to be here. It was kind of a strange series of events that got me invited. I worked with someone named Laura Coyle, who's a good friend of Jennifer, and said, hey, we need somebody to come give a talk. I love Texas. So here we are and all that. And it's rare that I've done a lot of public speaking about this telescope, but it's rare that I get to talk to kind of a STEM audience, and this is a great thing. And let me see, so anybody studying physics? Okay, good. And how about engineering, just in general? All right. And I understand you guys, you had to be here, right? This was required? No? Was it voluntary, mostly?
Yeah.
You wanted to be here? Okay, I think I'm beginning to see the picture here. Let's see, so you're STEM people. And you're all young, you look pretty healthy to me. Instead of going out today and doing something like, oh, I don't know, chasing the opposite sex maybe, chasing the same sex, I don't care. Chasing somebody, right? You chose to come here today for this hour to listen to me talk about the James Webb Space Telescope. And you wanted to do this, right? You chose to do this. Okay, that's because you're nerds. No, that's okay. That's a compliment. You see, when I tell you I'm a nerd, I've been one for years, but when I call you a nerd, that's a compliment. Because being a nerd is the best possible thing you can be. You want to know why? I'll tell you why. Because everything that takes place on this planet, everything that's good, that's useful, that's important, takes place because of this up here and not this here. Am I right? The movers, the makers, the shakers, even people that bring about positive social change do so with their minds, with their intellect, and not by how fast you can run or how far you can throw a ball. All right? There's nothing wrong with being athletic. I mean, many of you guys are probably athletic. I'm athletic. You wouldn't know it to look at me, but I'm an endurance cyclist. But there's nothing wrong with being athletic at all. I'm just saying we got to keep a sense of proportion. And what really matters is how smart you are, what you do with your head, your gray matter on top of your shoulders, right? Now, if we were animals, it would be different, right? Right? And what on the Serengeti, what do they call those little things that the predators are always eating? What are those things called? Those animals?
Gazelle?
Yes, gazelles. See, only a nerd would know that. Yeah. If we were gazelles, it'd be different, wouldn't it? Let's face it. Every day the jock predators, the jock gazelles, and we would get together and have a meeting and say, okay, today when the lions come to eat us, just make sure you run faster than the nerds. All right? And let's face it, those predators would be eating us like popcorn. But we're not animals, we're human beings. And in the human race, it doesn't matter about your physical body as much as it does your mind and your intellect. See, guys, you're king of the jungle, right? You're STEM people, you're physics, you're engineering. You know, you're top of the food chain. Do you see where I'm coming from here? Okay? You don't need to lot it over everybody, but I want you to understand that your mind is very, very important, and it's an honor to be here in Tyler, Texas, talking to the best of the best. All right? So when you get home tonight, get down on your knees and give thanks that you were given a mind, an intellect, because it's what separates us from the animals, and in your case, from much of the human race. All right. Okay, so that was my nerd talk. Let's see, we're good there. So anyway, I'm going to talk a little bit about the James Webb Space Telescope. Now this picture I got up here was the last picture we took of the telescope before it moved away from the Earth on its journey to the second Lagrangian point. And this was actually taken with a webcam that was put on top of the second stage to just make sure that the spacecraft separated from the launch vehicle correctly. It was completely accidental that we got this incredible image. I call this farewell web, with the Arabian Peninsula down there, and just beautiful. Just before this is right before the solar panel unfolded and the deployment sequence began. So here's let's see. Now we might want to turn the lights down just a tad at least. I'm going to show you a lot of pictures today, and most of my pictures, though, are not going to look like this, or like this one. The pictures I show are going to look like this one. Okay, a big gobbly mess, because the images have to look like this before they can look like this. So that's what I'm going to do. I'm going to talk you through the process, to tell you the story of how we started with a completely randomly deployed telescope and worked out how to move all the mirrors and everything so that we could get the telescope in a diffraction limited sense so that we would take these beautiful images. All all right? Now, of course, I didn't do this myself. There's a lot of people that worked together for many years. Some of them are on this list. So basically, I'm going to go into a short introduction. I'm going to talk about the overview of the Wavefront sensing and controls process, just cover a couple key technologies involved in this process, and then show you, go through step by step how we phase the telescope. And I want you to understand that whenever you see a picture that shows an image moving from here to here, in order for that to happen, a team of people on the ground had to decide that we needed to move this segment such and such. And those commands were converted into other lower level commands, were sent to the pipeline, were sent to whichever antenna in the world was as part of the deep space network, was talking to the observatory at that moment, got sent to the telescope, they got executed, images were taken, downloaded by doing everything backwards, and finally until this stuff went through the ground system pipeline and process and it appears on our computer, and so we can analyze it and see what happens. So every time you see an image move up here, that occurred, and that's why it takes months to do this instead of just hours. All right, so here's a picture of the telescope. Actually, this is a drawing of the telescope because we don't actually have any photos of the telescope in space. There's no light out there except for on the other side. But here's a couple, oh, there's a good picture. Yeah, I sent that to Jennifer, she put it in the flyer. If anyone ever wants a good definition of narcissism, just say taking a picture of yourself in a $10 billion mirror. Gold. Yeah, but that was quite a deal. Here's a little bit about the telescope. Most of you are familiar with the Hubble telescope, and you can see that the primary mirror is quite a bit bigger. More importantly, it's all those segments are numbered, and we know them like we know our children. Everyone has his own little peculiarities and everything. They're A's, B's, and C's, depending on the optical prescription. Now, as you recall, and tonight, you're going to get a very different talk today than I'm going to be giving tonight, but you recall that there was a big deployment sequence where this whole thing had to unfold like a transformer, because it was all folded up to fit into the launch vehicle, and it went through these steps that took about several weeks to be completely unfolded before we started this process. Well, once that deployment happened, we ended up stepping through what we call our Wavefront sensing control process. And each one of these steps is multiple days long and has a team of people and certain subject matter experts that were designed to do a certain part of this that played in on it. And I'm going to step you through this process more or less in its entirety. I'll be combining some things to save a little time, but by and large, we're going to go through this process here. Now, here's a picture of the integrated science instrument modules. This is where all the science cameras, people talk about how expensive the telescope is, but you got to understand we have 9 different science modes on this observatory. Rather than most spacecraft that just have 1 or 2. And the integrated science instrument module where all these various different instruments live. Here's a picture of NIRSPEC, the near-infrared spectrograph. This is a picture of the mid-infrared imager. And this is the near-infrared camera, NIRCam. This is an interesting thing about this. You notice the top and the bottom are very similar. That's because it's 2 completely mirror-image redundant instruments. This is what's primarily used to phase the telescope, so we had to be completely redundant. Electronics, hardware, filter wheels, everything. And here is more of this is the near-infrared imaging slitless spectrograph. This is a Canadian instrument. And by the way, I should mention that this project was a cooperation between NASA, between the Canadian Space Agency and the European Space Agency. So it's international. Now here's where all the science instruments live. And if you can imagine, you'll see, I think I've got up. Okay, here they are. There's the near-infrared spectrograph, the near-infrared cameras, the mid-infrared imager, and then the slitless spectrograph instrument. And these are fine guidance sensors. Now those are interesting because they're imagers. They take a picture, but not for scientific reasons. They take a picture, an image, so that we can control the jitter of the spacecraft. We can measure if the pointing is wrong and fix it maybe 30 or 40 times a second. Now this is a blow-up of the near-infrared camera. And as you can see, these 2 parallel modules are made up of 4 detectors each. And each one of those detectors is 2048 by 2048, which may seem small compared to your web camera on your phone, but remember, these are infrared detectors. These are extremely low noise, high dynamic range infrared detectors. And so this is really cutting edge. Primarily, we concentrate, and a lot of the images I show today are going to be taken mostly on this detector because it's near the center of the field of view of the telescope. And we also have beam splitters, so it passes the longer wavelength channels to another completely separate instrument within NIRCam, where it has single detectors for each module, and the pixels are twice as big, and we look at the longer wavelengths on those images. Now, a couple of things we had to keep in mind, and I won't dwell on these, in the process. We always wanted to correct the largest errors given at any moment. So we didn't want to go off and polish the apple in any one step before getting the glaringly obvious problems with the telescope fixed first. And we always want to try to improve the alignment of the telescope. Now, why is that? Well, when you move something, you never know. It may be the last time you move it. And so you want to make sure that you try to leave the telescope in as much of an aligned state as possible. We had to have overlap between each step and the next step so that we could guarantee that we wouldn't get lost out in some kind of algorithm space. You always have to worry about the telescope temperature. That's interesting. There's a cockroach running around the carpet here. I forgot about those in Texas. It's good to be home. I used to live in Abilene and Lubbock too. The temperature has to be stable, but also has to be cold enough so that certain detectors will work, right? We don't want to use the actuators too much, and we have to make use of the normal science modes, and we always have to keep into contract, into possibility or into contingency. Like, when you saw the movie Apollo 13, when that happened, when they had that error, they didn't just wing that, right? They went to a shelf and they picked it up off the shelf. It said free return trajectory using the LEM as the power source, right? So they worked all that out before any of that happened. It was completely planned. They had to improvise a lot of things, but by and large. So we always, a good part of the last several years has been developing contingencies that were never used. And finally, anytime we do anything that's going to modify the telescope, there needs to be at least 2 sets of eyes on that process in its entirety. Okay, here's the wavefront sensing and control room. And there's a couple of my guys sitting at the telescope doing some analysis. Let's go back to here. So I won't go into details here, but there's a wall between where the actual analysis is and everybody else. And I had them, that was me. I put that in there because I have ADD and I can really get distracted. So I wanted to be able to have a door that I could shut and completely lock out the rest of the world. All right, now, this all holds together by some software that we wrote. The WEX, the green thing there, is written in C and Python. The mirror control software and the wavefront analysis software are written in a language called IDL. I don't know if astronomers, if you're familiar with that, the interactive data language. It's kind of like MATLAB, right? And then we communicate with the rest of the ground system through that green box for the most part. Now here's some special hardware that we got to put into the science instruments, into the NIRCam. First of all, we have some weak lenses we got to put in the filter wheels that allow us to take the image slightly out of focus without doing anything to the telescope. So we just say, let's take it out of focus, so we just put in this lens, and now instead of a crisp image, you got a slightly defocused image. We also have some elements that we put in there that allow us to make spectra between pairs of segments. So we make a spectrogram of light just from 2 of the segments, and I'll show you how that works and why that's important later. Finally, we have a little lens that can be flipped into the beam that will make an image of the primary mirror. We call it, a selfie, right? The director of NASA said, oh, you mean a selfie when we were talking about the pupil image. And yes, that's what this does, and it turns out to be a very important diagnostic. Now, we're talking about wavefront sensing controls today. Well, what is a wavefront anyway? You ever kind of wonder about that? What does it mean to be a wave? I mean, obviously, if you have a drop in the water, you kind of know what a wave means. But what is a wave? Well, it comes down to this concept of an electric field. An electric field can be thought of having a phase and an amplitude. And the problem I have with this, and I struggle with this all through my college and even today, is I'm not even sure there is such thing as an electric field. I don't even know if that's real or not. Okay, so we're talking about the phase of the electric field when we talk about the wavefront. And the reason we have this concept of a wavefront or a phase, or an electric field for that matter, is because we're able to come up with this description of Maxwell's equations that seems to describe reality very, very well if we hypothesize the existence of an electric field. You can't measure an electric field. You say, well, of course you can measure it. No, all you can measure is the potential. Not even that. Differences in potential. 2 days ago, my car died on the way home from visiting my parents. What did I do? I took out a voltmeter and I measured the difference in potential across the battery terminals, 11.5. So, even still, so so you're not even measuring the potential, you're measuring the difference. But when you measure those things, you find that these equations describe reality very, very well if you hypothesize the existence of an electric field. In fact, it was the invariance of the form of these equations under something known as the Lorentz transformation that led Albert Einstein to hypothesize the theory of special relativity, by the way. And incidentally, the reason we have these equations is because some guy named Laplace solved this differential equation. So there, in the mathematical description, something came just out of pure mathematics. You have something that essentially predicts the existence of special relativity. In any case, I'm going to assume for the sake of an argument that there is an electric field, and we can talk about the phase associated with that electric field. All right, so what we're going to do is we're going to look at the optical system in such a way that we can measure the amplitude, which is the only thing we can measure in an imaging system, and infer the phase from that. And that's really what this is all about. So this is an important aspect of this, something known as phase retrieval. So we want the phase, which we're going to assume exists, even though it may not really exist. And all we can really measure, though, is the amplitude. You take an image with the thing, you look at the amplitude is like the geometry of the pupil, geometry of the primary mirror, and you can measure the amplitude, and we have to infer the phase from that. Well, there's this really interesting theorem in mathematics that says if you have a complex function, okay, so I got a of x plus I, b of x. And you can make some very simple assumptions about this function. First of all, it's spatially bounded. So in other words, you can draw a circle around that function, and after a while, it effectively goes to zero. It just has to fall over faster than 1 over x, all right? And secondly, that it doesn't have any discontinuities that would show up when you're taking a derivative. So you can continually take the derivative as much as you need to, and you never get a discontinuity. If those things are true, it turns out knowing A or B is enough to specify the complete equation, the complete function. So if you know the imaginary part, you can find the real part, and vice versa. Or, better yet, if you know the amplitude, you can find the phase. That is the magic of phase retrieval. In 2 dimensions, it works even better. It's a little less restrictive. All right, so this only works in theory, though. All right. First of all, it's a lot harder because you have noise. You have noise in the images you record. You have degeneracy. Remember, you want V phase, not just A phase. All right? But the main thing is knowing a solution exists doesn't give you that solution. All right? So basically, that's what we've been working 20 years on, is knowing how to pull these answers out, the phase out of the amplitudes. And all we do, I won't go into details here, but if you measure the phase in more than one plane, like say a defocused image or maybe multiple defocused images, and the pupil geometry, which is just the geometry of the telescope primary mirror, we start with that and we iterate back and forth between that pupil and the image plane, and each using a Fourier transform. At each point, what we do is we throw away the calculated amplitude and replace it with a known amplitude, and then iterate back and forth between those planes by using forward and inverse Fourier transforms. And if you don't know what a Fourier transform is, that doesn't matter. It means in MATLAB you just type FFT. Literally, that works. And lo and behold, when this happens, it yields the phase. We also know the image can't be non-negative and everything, and we use multiple focus positions. But this gives us the phase. Now, we use phase retrieval throughout this process in many places. Sometimes we use the secondary mirror to defocus the telescope, although generally you don't want to do that because, like I pointed out, that might be the last time you move it when you take it out of focus. And oftentimes we use these weak lenses which are in the science instrument to create defocus. All right? So let's see what else. I just wanted to throw this slide in here because it goes to show you that we hire interns, summer interns at Ball Aerospace, and I've had 2 interns working on this project, and both have done really, really well. One of them down here, Rebecca Elizabeth Carlisle worked on this algorithm to develop something that we use now throughout the commissioning process. It's extremely robust, and there was a paper written on it and everything. And that was her project, so it was pretty cool. Now, we're talking about moving mirror segments, and I want you to know that these mirror segments are mechanical devices. So here's the back side of it. Each mirror segment has 6 actuators that allow us to move it in 6 degrees of freedom. So we can move it left and right, forward and backwards. We can rotate it like this. We can tilt it this way. We can tilt it this way and move it in piston. So we can move the mirror segment in 6 degrees of freedom. And when you move those, it changes the wavefront, it changes the phase. Obviously, if you've got two segments that are lined up and you move one up a little bit, you're going to change the phase by introducing piston in it. But the thing is, when you translate or rotate or move these segments relative to where they are supposed to be, giving the optical prescription of the telescope, it creates aberrations such as astigmatism, power, focus. So astigmatism looks like a saddle shape. Focus kind of looks like a parabola. And you get those terms when you move it away from the design optical thing. Now, but likewise, if you detect the existence of those terms, you just have to move it the opposite direction, and you get the exact opposite. You can correct an error like that. There's a seventh actuator on the very back of this, and that is designed to change the radius of curvature of each mirror segment. So it's actually pushing and pulling on the center of the mirror, bending it to create like a contact lens shape, to create a little bit of power or take a little bit out. And keep in mind, these motions are very, very small. They're nanometers, not millimeters, they're nanometers. All right, everything's made out of beryllium, which is a very lightweight, very stiff metal. It's also very poisonous. You get it in your lungs, you get an allergic reaction, and it never goes away. So the mechanical actuators, I took these off of a website. Somebody actually was able to reverse engineer the actuators from little pieces of information here and there and produced a really good YouTube video about it. So if you go on YouTube, you can find out exactly how the actuators work. But the idea is they have a coarse mechanism and they have a fine mechanism, and it's set up such that if anytime you run out of range in the fine mechanism, the coarse mechanism is automatically engaged. But when that happens, you have about a 1 micron uncertainty in the length of the actuator. So you have to deal with that. The other thing we did is we made sure we measured the wavefront in a nominal scenario at each point in all the science instruments while we were still on the ground. And the idea is that when we make a measurement in space, we're going to subtract these off. Okay, so that we only act on what's associated with the misalignment of the telescope. And I will point out that we had a 1/6 scale model of the testbed telescope, and this was used to develop a lot of the algorithms to basically test different things before we committed to certain ideas and all that. And I had a conference once, I called this the JWST Mini-Me, and a reporter quoted me and I got in trouble for flipping it or whatever. But you remember from Austin Powers, the movie? Okay. So we've also done tons and tons and tons of modeling. Like I say, I've commissioned the telescope 100 times in software before we even got to the flight stuff. And this was actually very important. So starting off now, I'm going to go through the process. First of all, we deployed all the telescope and we put all the mirrors where we thought they were supposed to be. Now the reality is, of course, each of these mirrors is in slightly the wrong position. So when you look at a star, a bright star that's out there by itself, you're not going to see one star. You're going to see probably 18 stars, one for each mirror segment. And if you're not certain about the pointing of the telescope, you're not even going to see one star, you might see 0. Or what's even worse is you might see a star that's way over here that's now in your field of view because you think you're pointing at the right place, but you're really not. So we have to be very, very careful about this. But the first thing we did was deploy all those mirror segments to the right place. Now we're making steps that are like 7 nanometers at a time, maybe 50 nanometers, very, very small steps. And somebody, let's see if I got a picture of this here. I'll show you that in a second. After we got everything deployed, it turns out we were better than we had planned about getting things in the right place, about a factor of 5. So we were very conservative in our budgeting. But we had a couple of problems. We weren't able to point the telescope reliably at first. It would go to the wrong place in the sky, and by that I mean, tiny fraction of a degree, but wrong place nonetheless. And it wouldn't stay there, it would kind of wander around. And eventually we got that figured out, but it really complicated the initial steps in this process. And we had this fine guidance sensor, which is a flat mirror that moves around really fast to stabilize the image. That didn't work until later in the commissioning process, so we had to figure out how to work without having that mirror. So the mirror deployment was very, very conservative, starting off on moving each actuator like one step, and then maybe one revolution, and then a millimeter at a time. And somebody made the comment that actually grass grows faster than the mirrors were deploying. And so our project scientist, Jane Rigby, made us a chia web, and we watered it, and sure enough, the chia seeds were growing faster than the mirrors were deploying by quite a big margin. So the first slide image. So what we did is we pointed the telescope towards the Large Magellanic Cloud, and we took some images. And here it is. This is the very first image. This is just my cell phone taking a picture. You can see there are some images there that look very, very aberrated. Everybody was happy that had light on the detector, the cameras were working, but I was very concerned, and all the optics people were very concerned. We thought we had really screwed up the telescope. And it wasn't until Super Bowl Saturday that we realized, no, this was just a perfect storm. Secondary mirror being in the wrong place slightly, and the segments being in the wrong place to create this. But for several weeks, we were actually quite concerned. Let's see, oops. Okay, here we go. So then, once we knew we had captured some light, we pointed the telescope to a bright, isolated star, and then just started taking images and stitching them together. And here's what we got. This is actual data. And as you can see, we weren't far off. We weren't sure if we would even see it. And there it is, almost right in the middle of our pattern. And sure enough, if you look and you count, there actually are 18 spots there. Later on, we'd find out which one was which. So I could number those segments. And these are the wings. Now, in the deployment sequence, it's like a drop leaf table, the wings deploy, so that we would expect those to be a little further off and to deploy together more or less. And you kind of see that reflected here. But when we looked at this, we realized that there was obviously a focus bias, so we wanted to put the secondary mirror in the right focus position so that we could get the rest of the commissioning done. And here's what, see if I click on this. Okay, there we go. So this is stepping the secondary mirror through different positions and taking an image at each point. And we're just trying to figure out where the best focus is. Now, I was relying on the pointing being stable, but as you can see, it is not stable during this process. So the problem is, in analyzing these, I didn't know which segment was which. So I picked just one of these, and I did this phase retrieval stuff we talked about. And as it retrieved the phase, you can see it's trying to draw like a little secondary mirror support structure in the middle of the phase that is not part of my model, because I didn't really, that tells me that was segment 12. Well, once I knew that was segment 12, I know how segment 12 the images were supposed to move, so I was able to shift all these tiles accordingly so to make segment 12 lined up, and lo and behold, all the other segments are lined up as well. So now, based on in the upper right there, that's modeling, that's simulation results, I was able to figure out which segment was which within this pattern here. Cool, huh? And anyway, then we went off and did something known as segment ID to find all the ones we hadn't detected yet, and that's where we just point a certain place in the sky, and we take an image, and then we move a mirror segment and take an image again, and we figure out, basically which spot moves when we tilt a particular segment, and that tells us that spot is part of that segment, right? It's not rocket science, but it is a very, very involved bookkeeping problem, and when people would simulate this, that's where they make the mistakes. And particularly, it was somewhat problematic because of the pointing difficulties that we had. As you can see right now, I'm just stepping through one at a time. There you saw a segment move, another segment move. All right, so eventually, we're able to figure it out. But and there's an example when I take an image and subtract an image from it. You get some noise, but it's very clearly which spot moved there, you can see. And so now I know that was segment 2, for example. Right? And here's what the user would look at. So we do all the segments, but the problem is because of the telescope just was kind of pointing randomly throughout this whole process, all of our bookkeeping was completely lost. So we had to do this manually and just very, very carefully figuring out, okay, we got to do the right-hand rule and all that stuff. We got to move this segment like this to get it to come to here. And sure enough, we want to tilt all the segments so that everything comes to that center of the field of view where the crosshairs are. And we also pointed the observatory so that detector would be on that part of the sky. And lo and behold, we looked at this and 18 spots appeared. Now they were supposed to appear in the middle of the detector, and they were supposed to be in a tight little array. That's okay, we knew we had some pointing uncertainties, and 5 days had gone by since we took that first mosaic. And so the elongation of all the spots like this is because the temperature was changing the whole time. That's just the warping of the backplane of the telescope during this process. But the main thing is we saw 18 spots appear, and then what we could do is we could then tilt these to form an array. There we go. So that we can do some work on the individual segments. So we took that image, we colored it blue, and released it, and it went viral. Okay. So then what we did is we did something using this phase retrieval again, just like this, except now we're going to use the secondary mirror to defocus the telescope, and we're going to apply phase retrieval algorithms on the individual segment images. There we are at minus 400, 0, plus 400. And this is what we got. The phase is shown at the top, and then there's a high-pass version of that on the bottom, so you can see some of the aberrations here. I'm not sure if I can push this middle thing, so give me a laser. I don't know, I guess not, that's all right. You can see here, some of these segments have like a little donut-shaped thing in the middle of them. Okay, that's because the radius of curvature actuator is cranked really hard, and that's a print through of it. Now we expected that to be on 2 of them because we accidentally polished those to the wrong radius of curvature and just opted to leave it there rather than remake those segments. But there are 2, the upper right and the upper left, that are not supposed to be that way. This was a bookkeeping error. We don't know how it happened, but they got sent to the wrong radius of curvature. So we had to fix them at this point, and that was quite a bit of a discontinuation having to make this decision, but we did. So we made some radius curvature adjustments on those. The secondary mirror was way the heck off. There was a millimeter in each axis. But you think about it, the secondary mirror deploys like this. What are the odds you're going to get that to better than a millimeter? That's the way I thought of it anyway. So then we did some rotation of the mirror segments as well, and then any focus that we saw in the wavefront, so a parabolic shape, we decided we would interpret that as a piston error, so then we moved the segments up and down in piston. And we started off with quite some big errors, and we ended up with 58 nanometers root mean square. So when I say RMS, that means like the standard deviation. And that worked really well. Here's the images before and after. As you can see, the center 1 and 0 now is very, very crisp, very, very aligned. All right, so then we're going on to something known as image stacking. What we mean by that is we want to move the segments so where they are so they fall right on top of each other in the middle of the detector. Now the problem is we've got some big piston errors between the segments, and they're bigger than the coherence length of the light that we are analyzing. So we can't use this phase retrieval really to do this process at this point. We have to use just center of gravity calculations, centroids, and you'll see how this works. But there's a couple other constraints too. We can't waste all of our fine range in the stacking process. We have to get to the center where it's supposed to be stacked, with most of our fine range left over for reasons that are not likely to become obvious at the moment. But let's show you how this happens. So we start off, we move the center segments to a little tiny array, measure their positions, move them in the center, and recenter the fine mechanism of that option, and then move it out. Then we go to the next group of segments, and we move them in, recenter the fine mechanisms, move them out, measure the centroids, and stack them in perfectly. And now we guide on the center image, and we move the final corner mirror segments in and measure their positions and stack them perfectly. Now we got a telescope that's perfectly aligned except for piston errors between one segment and the next, and they're still quite large at this point. But even still, it allows you to take some pretty good images. First of all, you can use that pupil image lens and take a picture of the primary mirror, and we did. And then secondly, you can get a pretty good image of the sky. This is the Large Magellanic Cloud. Now granted, this has a resolution of 1 mirror segment, not the complete telescope, but still, that didn't keep me from putting this on the lock screen of my iPhone, Still there, go ahead.
Is that the 2048 resolution?
Yes.
Okay.
Yeah, but each pixel's each star is like 10 pixels across. It's not even close to being fraction limited. Then we went on to something to coarse phasing. Now this is a fun little algorithm. So here's the idea. Here's how it works. Remember, we've got some elements that we can put in a pupil wheel inside of this science camera, and each of those little rectangular things are diffraction gratings. And they create a spectrum, but only using light from those pair of segments. Now, if I were to just start off and I took an image with just a single subaperture like this, it's going to give me what we call a point spread function, or an image that sort of looks like that little rectangular thing up there. And that's, that just falls out of it. You can imagine you get square look images if you have a square pupil. Now, if I were to move one of these segments a little bit, that's what you get. If you're only going to have small piston errors, like 1/3 of a micron, this is all we would need. Just take a picture. I can tell you exactly what the piston error was between those two segments. But the reality is, if I go to 1/2 a micron, I'm back where I started. You see it's highly degenerate, because in the wavefront, the phase, the sine and the cosine of 2 pi is the same as the sine and the cosine of 0. So you lose information, right? There's 1/2 a micron, there's 5 microns. It looks exactly the same. at a particular wavelength. But if I disperse the light across the detector and look at different wavelengths, I get a different pattern for each of those wavelengths. So what I do is I take this spectrum, this is just like this spectrograph, and I analyze that little barber pole pattern thing, and that can tell me how big the piston error is between the segments for that pair of segments, and which direction it's off. Now, if I do this with a lot of different pairs, you can set up a system of linear equations, do a single value decomposition to get rid of this is all linear. By the way, all the math I took in college, all the math, linear algebra is the most important. It's consistently been the most important. Thought I'd throw that out there. But now if you have really big piston errors though, what you end up having is so bad that it looks exactly the same as being perfectly phased, right? So you got to be careful about that. So anyhow, we did this. We have 30 different measurements because we have 2 different sets of the modules at an angle. And so 30 different piston differences that we can measure this way. And we throw it all together, and here's what those 10 spectra from each little element look like. And if you zoom in on here, you'll notice on one of them, the second one from the top, it's too big, right? I was not able to see it. But if I go over to this other detector, which has longer wavelengths, then you can see that you do indeed capture those little fringe patterns. It was like close to 400 microns off, which is a big piston error. So we ended up making these corrections and applying those to the telescope. And then, of course, that engages all the course mechanisms. So now we're back to kind of a mess, but we can fix it all. Now, the next thing we're going to do is we're going to measure the field dependence of the wavefront errors, because if you put the secondary mirror in the wrong place, it's possible to fix what that does to the wavefront with the primary mirror, and you can have a perfect image of one field point, but as you move away from that field point, it can get to be really, really bad. So if we waited till we got to the end of the whole commissioning process to address this issue, we might find we have to make a big correction, and we've done all this work for nothing, right? So we want to tease this out early on. That's why I came up with this thing called the coarse multi-field. And what we do is, well, let's back off a little bit. So the idea is this, is the wavefront at any field point x and y can be written as the sum of 3 terms. First of all, it's whatever you got is common to the whole observatory. Like if you got segments in the wrong place, right? That's common to every field point. And then finally, this is the field dependence that you would get with a perfectly aligned telescope, and this is the wavefront you get because you've misaligned the telescope. Obviously, I want to find and fix this last term. These are all measured. This you know from a model, and this is what we're after, and obviously you just have to subtract those from there to get that. Well, it turns out that this equation shows that you can write that field dependence as a linear combination of the field location you're talking about and the errors in the positioning of the secondary mirror. I mean, this equation makes it possible to align the telescope. It's just, in the biggest defiance of Murphy's Law ever, it's actually a very simple problem from a mathematical standpoint. All you have to do is measure this field dependence of the errors, and you know exactly what's wrong with the secondary mirror. You put that secondary mirror where it belongs, and and then you adjust the primary mirror accordingly, and the telescope's aligned. So what we did is we did something known as a coarse multi-field. We put the spots in a little tight pattern like this, and then we move it around to different points in the field to see how those spots move as a function of position. And that tells us the aberrations, the errors. Now, so here's what we're doing. We're going to start off coming out of the coarse phasing corrections. We're going to move these spots into this little tight array. And we only got partially the way there. So we're going to clean things up a little bit. All right. And there we are, and then we move around and we measure where all those things fall relative to this little one that's kicked out for guiding. And this allows us to calculate the focus in the astigmatism. There's a catch, however. It turns out that the field variations within the science instrument are bigger than the stuff we're trying to measure in the telescope. And if we acted on that, it would completely screw things up. So it turns out that if you take this array and you make a second set of measurements, after inverting this array, so everything goes through the origin and across the other side of the array, if you make these measurements like this and average them with the previous ones, the result you get is perfect. It exactly cancels out all these aberrations, and at least in my brain, that's what it did. And it turns out I was right. So what we did is we made these measurements. We had some huge errors. The Y translation needed to go another 0.5 millimeter almost, and there was a huge tilt. And we were forced saying, okay, should we do this? It was 2 o'clock in the morning, and I said, all right, just tilt the mirror, we'll get it, it'll work, right? But I was actually quite nervous about it. And sure enough, once we measured these errors again, the second time through repeating this whole process, the only thing that was left was noise. And we all have our moment when we were happy and we were glad everything was working. This was mine. It just thrilled me because it wasn't really possible to test this theoretically or to test it through simulations. We had to get on the real telescope to test it, and it just performed beautifully. So after that, we went back to do global alignment one more time. And so we're in this array. We're happy with everything now. And so now we're going to move everything back out into this big array. And we're going to move the secondary mirror to take the images out of defocus and just clean up whatever is left. And here we are, stepping through the focus. This is very small errors left now. So we make some radius of curvature adjustments and a little bit of clocking and radial translation of the mirror segments, and then make the measurement again. And now we're getting down to almost a perfectly aligned telescope, 44 nanometers root mean square, and this is really, really tiny. Look, here's something to think about. Think of the primary mirror as being North America. One of those segments is Texas. The errors we're talking about are like an anthill. Fire ants, granted, in Texas, but they're just an anthill. So anyway, we were so happy. Here's a comparison of that measurement on the left to what we measured on the ground. Now, actually, it really wasn't measured on the ground because of gravity. We never could really measure it, right? We had to make a measurement and then back out all the gravity sag and the calculations and stuff. But it's essentially perfect. It's almost a perfect agreement. There's a couple noticeable exceptions. Obviously, what we got in space is a little noisier. But if you're looking about the 11 o'clock position up there in the space measurement, you see a little divot, and then it's not there on the right. That's one of the first micrometeor strikes that we noticed. And these are happening all the time. Every couple of weeks we'll see a very pronounced one. But you also get an idea that it's kind of small relative to stuff that's already there, right? So we do get hit by meteors all the time, but most of them are okay. So then we're going to do image stacking again, except this time, rather than do all that bouncing around with centroids, we're going to use phase retrieval. But first of all, we got to move all these segments from where they're current position to be exactly in the center. And now you want to be careful you don't move it to the wrong place, because if you end up tilting all those mirror segments, you've effectively forced yourself to put a bunch of piston error in it. So it has to go right in the middle of this array, right exactly on those crosshairs. And this is what happened. I went to bed. Yeah, it's a mistake. Anybody can do it, but no problem. We just moved it back, to the right place. So anyway, so that we got most everything there. You notice we left one out. That's for the fine guider to work. So the guider captures that light from that segment, and it controls the pointing of the telescope based on that. So then we start off and we take these images at the top. Now there's 6 different focus positions, and we run the phase retrieval algorithm. We come up how much we have to tip and tilt those segments to fix it. And you just go through one step. Now we're only doing the tip tilt. We're not doing any piston adjustments at this point because we're going to measure that in a second. But then you get everything perfectly aligned. Now that most of the piston errors are corrected, see, this is before on the left. Look at the difference in coherence, because now we're well within the coherence length of the light. And we are, so now you see full interference from one segment to the next, and in the PSF, point spread function. All right, so then what we're going to do, this is just the phase retrieval, what we saw, getting the tip and tilt correct in each segment. So we repeated this whole course phasing thing, except this time we're doing things a little different, because as the piston errors get close to 0, this process becomes less and less accurate. So what we do is we intentionally add some piston into each of these segments as we take the measurements, and then we subtract it out of what we measured. And here's another example. Now this time, much smaller corrections, -4 to +4. That's still big enough to engage the course mechanism, so we got to do this one more time. So we did it one more time. Finally now, we're getting really close. Tiny errors on this thing. And we took the course phasing measurements again using our dispersed fringe sensing techniques, and this time I scrunched them all up so you could see the presence of that extra piston that I added so that we could measure it. See, if it was just a straight line, you couldn't measure it. And now they're very small corrections, less than a micron, does not engage the course mechanisms. And so what we do is we now do this fine phasing thing, the phase retrieval algorithm, one more time, except this time to correct the piston errors as well. And take a look at the images that are right here, in this third from the left. As the piston errors are corrected, you'll see that it gets brighter and brighter. In fact, it's just completely saturating the center because we can't capture that entity focus image at the same time. And at that point, it's effectively completely phased. At the end of the day, we had 46 nanometers root mean square, which is really, really small. And we took our first image, and this was a fun moment because what we did was we got everybody in a room and put up a big screen like this and fixed the ground software so that no human being would see this first image until everybody got to see it. All right, so there's no sneaking around back on the computer, And so this is what we had. We intentionally pointed at this star. This was in Ursa Major, and it is a bright star. But we said, okay, we're going to let it saturate. We don't care. Because what we really wanted to see was all those galaxies in the background. And this image had 241 galaxies in it. The first image, the first diffraction limited image with Webb had 241 galaxies in it. One of them, that one there, even has a supernova. Captured a supernova in the first image with the telescope. By the way, you have to try to not make scientific discoveries with this. It's just because, boy, anytime you have an instrument that enables you to look somewhere that no one's looked before, everything you see is a scientific discovery. So then, how do you celebrate that moment? You guys will appreciate this, at least I hope you do. Well, this is James Webb. He's the guy who the telescope was named for. Anytime you get into a public eye like this, there's going to be an element of controversy associated with it. Yeah, we'll let that live as it does. But if it wasn't for him, we probably wouldn't have made it to the moon. He really was a remarkable man, and he was born in 1906. Okay, so was this bottle of cognac. And me and a buddy that I worked with in the project, we're the proud owners of this bottle of cognac from 1906. And I don't actually drink, okay, but I made an exception for this time. The director of Aura bought some special glasses for it, So there we are. It was a big glass. It was a big bottle. Everybody got a shot. About 70 of us. I had about 4 or 5 shots. And not being a drinking person, I got very tipsy, which is a grown-up way of saying drunk. And I remember I tweeted to a friend of mine, I wish you could see the universe from my perspective. We are surrounded by a symphony of creation. There are galaxies. And anyway, so later NASA asked me for a quote, and I think, well, I say a quote, and I remember that tweet, so copy, paste, send, it went viral. It was in Forbes magazine, it was on CNN, oh, what a beautiful poet. Well, they don't know that I was toasted on pre-prohibition alcohol. But anyway, so there we are. It was quite a deal. Let's see, and here was the image we took after, and this was the Large Magellanic Cloud. Let's see if you can see the difference. Now it's much sharper, right? Because now there's only 2 pixels across each point instead of 10. And we did one more measurement where we did this phase retrieval, except at multiple field points amongst the various science instruments, because we wanted to take one last measurement to be certain that we have the telescope aligned at every field point. And this is hard. Very hard to do because, first of all, the instruments don't have a way to go out of focus. So we have to take the telescope out of focus to make this measurement. And secondly, a lot of those instruments are their broadband sensitivity, so that greatly complicates the phase retrieval algorithms. It's all software and everything, but you can see NearCam, what we've used up to point, is essentially monochromatic because of the filter we chose, but the others are broadband. And here's an example of some of the images taken on the various science cameras, out of focus. You can see you get a very different looking thing. And then, but we ended up, it just turns out there didn't need to be any corrections. It was all fine. It was well within what we planned and budgeted and all that, so we left it there. And finally, we did one more thing, a thermal stability test, and this is what I'll close on. The idea is that, this telescope is very cold. It's like 50 Kelvin or so, and any temperature gradients or changes will cause the mirrors to move. So what we did was, just to see if that wasn't the case, we would point it with the sun shield at one angle relative to the sun and leave it there for like 5 days. And then we would move it to a completely different orientation and leave it there for like 5 days, just to see if the primary mirror and everything stays aligned. And we're banging off images just like we've been using all through the talk to see if that's the case. And somebody had this idea. They said, okay, great, so it's thermally stable, but how do you know that the telescope isn't rolling during this whole thing? You got this fine guider to keep the telescope pointed in the same place. all right, you keep that star there, but the whole telescope could be turning about that point. Well, it's a good point. So we said, well, I know what we'll do. We'll use the primary fine guider channel to maintain the pointing, but then we'll use the redundant channel to just bang out, like, I don't know, 20-minute integrations, 20-minute exposure times throughout this 10-day test. And so we did that, and it turns out that if you have that fine guider, if you remember, it's sensitive from 1 to 5 microns. You're at 50 Kelvin, there's no competing light sources, and you got a 6.5 meter telescope. Even one of those 20 images is going to see unbelievably deep. Well, guess what happens when you average 100 of them together? You end up with the deepest image ever taken, and it was completely accidental. This is by far way deeper than the Hubble Ultra Deep Field. It sees things just may as well be back at the beginning, the Big Bang. This image, the co-added, stacked image, I sent it to an astronomer, galactic astronomer at UCLA, and he estimated that the single image contains 15,000 galaxies. And if you look at the tiny, tiny part of the sky it was seeing, let's see, zoom in on this, for example. See, everything you see there is a galaxy. And it works out that there are probably 300 billion galaxies that are available to Webb, that we could actually, if we chose to, could actually look at that galaxy in the entire sky. And this, the realization of that there is no dark sky. Dark sky is a myth. It's galaxies everywhere. It was really quite an emotional experience for me. Everybody reacts to this kind of stuff differently, but for me, I pictured all these galaxies out there singing. That's just in my brain the way it works. I pictured them singing. I pictured the universe as expressing joy that after all these millennia we could finally see them. And that's what I'm going with. All right. So anyway, galaxies everywhere. I think that is the end of the presentation. No, I have to close on the what is this? Oh, it's a pretty picture. I forget. The Tarantula Nebula. That's it. The Tarantula Nebula. All right, guys. Thanks for your attention. You've been a great audience. I think there's questions, but let me, I always like to take a picture of the audience. There, YouTube. Facebook. All right, are we answering questions?
Yes, I'm gonna turn the lights up a little bit for this part. So I've got the handheld, so I'll come around, but questions?
Testing. So if these are all infrared cameras, and since infrared isn't visible to our eyes, how do you decide what colors to make the visible pictures that we see here?
Whatever you feel like. Yeah. I mean, usually the longer ones are red, and the shorter ones are blue.
So is this like a corollary thing?
Well, I mean, there's no set thing, but I mean, except for that, if you've got, say, 1 micron, 1.5, and 2 microns, that would be, red for the 2, green for the 1.5, and blue for the 1. If it's 2 to 5, 2, 3, and 5, the same thing. You use the red for the longer ones. That's all. Yeah. Good question, though. It's a question everybody has. Very true.
Well, I think if there are no other questions, there is more pizza. But let's thank Dr. Acton one more time for coming out. And just a reminder, there's going to be another public lecture this evening in here at 6 o'clock. And after that, there will be a reception and a star party over at the planetarium. So y'all are all welcome back for that.
And what I did today will be 2 minutes in that talk. So.
Excellent. So yeah, come on back for more stuff. Carry on.